That's weird.
Yo, bro, do you actually know the physics behind that?
No, man, I have no clue.
Let me show you. Follow me.
That's kind of weird.
Yo, how did they build that?
I could show you. What the heck?
Cool. Była za tu? Ow!
Hi, my name is Mahad Khan and welcome to Crash Course Physics Honors. So previously you just seen my groupmates and I build the actual ball in the ball experiment. We built the model, but now we're going to show you a way to estimate the degree angle of the ball given different speed levels. So right now we're going to draw a quick diagram of the ball and the ball. So ball right here, and then let's just say this is the ball. Right now there are three forces acting on the ball. There is the normal force, gravitational force, and centripetal force. And this line right here for the normal force could also equal the radius of the bowl. The radius of the bowl is equal to 0.073025 meters. And this right here, the line for centripetal force, could also equal the radius of the ball itself. But the thing is, since the ball is always moving in a circular motion, we don't know what it is. So we have to label it as R for now. Alright, so we're gonna solve this equation by cutting this into horizontal components and vertical components. So let's solve the vertical component first. Alright, so if we have an angle theta right here, for the vertical component we're going to do a cosine. So cosine theta, cosine adjacent over hypotenuse, so the adjacent is the force of gravity divided by the normal force. We could multiply the normal force to the other side to get cosine times the normal force equals the force of gravity. And according to Newton's laws, force equals mass and acceleration. So this force of gravity can be rewritten as mass times the gravitational constant. And the gravitational constant, as we all know, is 9.81 meters per second squared. So this the vertical component, it can be rewritten as the normal force times cosine theta is equal to mass times the gravitational constant. And now we'll write it in terms of the horizontal component. So horizontal component. Horizontal component obviously would be sine since it's opposite over hypotenuse. So it would be sine theta is equal to the centripetal force divided by the normal force. Same thing, multiplied by normal force equals sine theta times centripetal force. Once again, Newton's second law of force equals mass and acceleration. So centripetal force is equal to mass times centripetal acceleration. And centripetal acceleration is equal to velocity squared divided by radius. Mr. Khan, since you're doing circular motion, why are you using linear velocity? I mean, it's going in circles, right? Don't you want to use angular velocity? You're right. Since this V represents linear velocity and we're dealing with circular motion, you can't use that. So we use something else called omega, which measures circular velocity. So omega, which is written as W, can be written as velocity, linear velocity divided by radius. So in this case, since acceleration is equal to velocity squared divided by radius, you would write omega squared times radius, because omega squared is equal to v over r times v over r, which equals velocity squared divided by radius squared. And this r is used to cancel out 1 to get velocity squared over radius. So you can rewrite acceleration as omega squared times radius. So now we can rewrite the whole thing. We can rewrite as normal force times sine theta is equal to mass times omega squared times r. Well, look, we don't know the lowercase r because, as I said before, r is constantly changing. So we would have to rewrite r in terms of something else. Well, look, you can rewrite r in terms of sine theta is equal to opposite lowercase r over hypotenuse uppercase r. And then you can rewrite as r sine theta equal to lowercase r. So if you sub this in over here to get normal force times sine theta is equal to mass times omega squared times r sine theta. And this is the horizontal component. And now you have to substitute both in to get the final equation. So I'm going to erase some of this. So now we have to do substitution. So now that you have both components, this one being the horizontal component of circular motion and this one being the vertical component of circular motion, you can start to substitute. Alright, so you have this equation, you can rewrite it in terms of normal force. So to do that, you take normal force is equal to mass times gravitational constant divided by cosine theta. Then you plug this baby right here into normal force. So then we would get mass times gravitational constant divided by cosine theta times sine theta is equal to mass times omega squared radius sine theta. Now this is where the fun begins, because now you start to cancel stuff out and it becomes way simpler. So mass cancels with mass, sine cancels with sine. And what are you left with? Gravitational constant divided by cosine theta is equal to omega squared times radius. And now you want to rewrite in terms of cosine, obviously, so you could rewrite it as cosine theta is equal to the gravitational constant divided by omega squared times the radius. And obviously you don't know the angle measure because that's what you're looking for, so you would have to take the inverse of cosine. So you get theta is equal to the arc cosine times the gravitational constant divided by omega squared times the radius. However, this equation measures the angle measure in radians, and we want to do in degrees given that we have a protractor. So to go from radians to degrees, you have to multiply by 180 over pi. And this is our final equation. And you might be asking, Mahad, what do we plug in for omega? Because omega is measured in radians per second, and you're measuring in RPM, which is rotation per minute. And I got a fix for you. So you would have to take your RPM values times 2 pi over 60. 2 pi because there are 2 pi radians per rotation, and 60 because there's 60 seconds in a minute. Once you do this, you could have the omega, then you just start plugging stuff in, and then whatever omega you plug in, given the RPM, you would get this certain degree angle out. And that's all it is. See you next time.
Push the bowl down in so the balls go to the edges.
Yeah, I got it.
But then it doesn't go because then it's like, there.
Okay, let's see.
Oh.
It's a good regular move.
Do you feel that it's...
Yeah.
Yeah.
Yeah, you can slowly.
Yeah, let's start slowly.
Oops. Yeah, now go.
Take one.
Faster.
See? There's more stuff. Nice! Yeah! Oh, there you go.
maximum speed. Maximum speed 690 RPM. Let's see if we can get it.
Safe to say 88.
Wow.
So quiet. That's crazy. So we recorded all of our actual values for the degree measures based on our RPM here and the expected values, and then we plotted them onto this graph.
So as you can see, this red line right here, which kind of resembles a Lin function, is the equation that I showed you guys before. It's the graph of it. So you plug in the RPMs and you get the expected angle out, and these data points are our data values, which Alex will explain right now.
As you see, all of them are actually under the theoretical line we have, which are contributed from errors that we might have made.
But overall, the data pretty much follows the pattern that we expected, with a couple minor errors here and there.
As you can see, the data gets closer and closer to the theoretical value as the RPM increases. This is because as the RPM increases, the angle gets closer and closer to 90. Like, this big increases when the RPM is low, but when the RPM is high, it gets slowly increasing until the angle reaches 90 degrees. Yeah.
The angle will actually never reach 90 degrees. It approaches 90 degrees as the RPM approaches infinity, but it will never actually fly out of the bowl in ideal conditions, assuming no bowl wobble.
However, these are not ideal conditions, obviously, as the data values are not perfect, and this can be attributed to certain errors, which Dan will explain now.
So some of the errors might be friction that we didn't account for, or the ball not reaching its full speed, like we didn't give enough time for the ball to actually catch up with the bowl. And some things might just be human error, like the camera might have been positioned incorrectly, and we might have just read the degree measure wrong.
But as you can see, the data pretty much follows the theoretical data, so pretty good. And then the average percent error is 6.04%, which is pretty low.
We had a very high percent error in the beginning, but as we got closer and closer to, as we got higher and higher on our RPM values, our percent error got much, much lower, almost 0.
So I'd say a pretty successful experiment.
I'd say so. If you'd like to take a look at the graph for yourself, you can pause the video right here. Otherwise, keep watching.
Alright guys, I'm going to explain the code for the Arduino setup. Alright, so the first 2 lines are just included to initialize the library that we need to control our 7-segment display. And the 7-segment display is just like the clock display that shows the RPMs for the motor. And it looks something like this. Alright, for the next section, we initialize some of the other variables we need. We set up our motor's RPM sensor to pin 2, and we also define variables for the RPM value, a counter for rotations, and a value for the amount of time passed. Okay, and the next section of code, we declare our interrupt service routine, or ISR function, and I'll explain that later. For the next section of code, this is actually our setup function, which is called once at the start of the program. Here we initiate serial communications to read our RPM values, and we also define some other variables for our 7-segment display to be able to display the actual RPM values in real time. Alright, in the attach interrupt command, we begin to monitor when a change in input from the motor's Hall effect sensor is detected. So this Hall sensor measures when a change in the magnetic field is detected, which can be useful in measuring the motor's RPM. So whenever a change in input is detected, the ISR function is run to add to the counter with our number of rotations. And the rest of the variables are given a value, and then the setup is complete. So the next section is actually a loop function, which will constantly run the entire time the program is functioning. It displays the RPM value to the 7-segment display and calls for our calc RPM function to be run. So the next section is our calc RPM function, and it checks to see if a second has passed. And after it does, it stops recording pulses from the motor's Hall sensor. It calculates our RPM value and either prints RPM as 0 if the motor isn't moving, or prints the RPM as the calculated value is a non-zero value. Our counter is reset to 0, and the past time value is set to the current time so that the RPM can be recalculated. The digital pin now begins recording the pulses for the Hall sensor again, and then the cycle keeps repeating.
So I'm going to be explaining the wiring and circuitry behind this whole machine. We start off with our battery pack right here, which has 8 1.5 volt batteries for a total of 12 volts. The current flows through this positive wire to the breadboard and powers this whole line. The current flows through the resistor into this positive wire, which goes to the potentiometer. Then the potentiometer adds its resistance to the current, depending on what setting it's at, which supplies the current to the motor. The motor rotates and the current flows through this negative wire back into the potentiometer and then back to the negative terminal on the breadboard. The circuit is completed when the negative wire from the battery pack is attached to the negative terminal on the breadboard, so the current can flow as a complete circuit. Then we have a 9 volt battery that's powering the Arduino board, which controls our motor's Hall effect sensor to determine the rotations per minute, as well as the RPM counter on this LED 7-segment display. The Arduino board supplies 5 volts to the Hall effect sensor so that it can run, and then the circuit is completed when this ground wire is attached back into the Arduino board. If If you're not familiar with a Hall effect, it's basically the phenomenon that occurs when a magnetic field is applied in a direction perpendicular to an electrical conductor. So in our case, the magnet on top is spinning next to the electrical conductor, which has current flowing through it. When the magnet approaches the conductor, the current is disrupted, creating a voltage difference. The amount by which the magnetic field is disrupted can be measured and actually turned into an RPM value for our motor. The motor outputs its data through this yellow wire, which is connected to the digital pin 2 on the Arduino board. This is where it reads all its digital data, and we can calculate our RPM from. Digital pins 3 through 13 are used to power the LED 7-segment display. Digital pins 3 through 9 are segment pins, which control each of the 7 segments you see here. Digital pins 10 through 13 are the common pins, or the digit pins, which control which digit is being displayed at what time. The display cannot actually display all 4 digits at once. It has to cycle through each of them at a very fast speed, which we've set to 1 millisecond. So these 4 pins control what digit is being used. That's pretty much it for the circuitry. If programming was the digital half of this whole control system, then wiring and circuitry is the physical half. So, you guys get it now?
Yeah, I think I get it.
What's physics?
Thank you.